Hello, I'm Professor Fred Coolidge, and we're going to go over Chapter 9 in the book, Analysis of Variance, affectionately known as ANOVA. ANOVA. So you'll usually see it abbreviated ANOVA. And ANOVA is going to be essentially an extension of our independent t-tests. We're going to have more than two groups usually, and we're still going to, the parameter of focus is going to be the means of the three groups. And so what we're going to do, our null hypothesis is going to be, the null hypothesis is that the mean on this dependent variable for group 1 is not different beyond chance than the mean on the same dependent variable for group 2, group 3, et cetera, et cetera. We could have more groups if we wished. And our alternative hypothesis is that at least one mean is different from one other mean. So they don't all have to be different from each other to reject a null hypothesis. Just a pair of means are different. That's enough for us to reject the null hypothesis. So we'll state the alternative hypothesis is HO is not true. And we can't state it in symbols because there's just too many possibilities. And that's why ANOVA is usually considered an omnibus test, because it's testing lots of different possibilities here. We're going to test this hypothesis with a new distribution, just like the t-test gets its name from the t-distribution. This is going to be tested with the f-distribution. And the f-distribution is a little bit different than the t. It's not perfectly normally distributed. It looks like this. This is still frequency over here. Here, let me erase this ANOVA, the nickname for analysis of variance. So we got frequency over here, and here's what it looks like. It's a skewed right distribution, and 5% of the area under the curve, this 5%, here's our f values along here, and this about here is about 1, and f equal to 1.0. And if our obtained f value from all these numbers falls out here beyond this value, this is going to be our f critical value, let's say at 0.05, which is the standard level of statistical significance, then we'll reject HO. If it falls anywhere in here, we'll retain HO. And the curious thing about analysis of variance in the f distribution is if there are no mean differences except chance, tiny little differences in these means, sample means that we'll use to test this hypothesis, there's only chance differences, then the f value will be 1, not 0. Okay, so let's give an example here. And let's say we're going to test a new drug for Parkinson's patients and see if it reduces the number of symptoms. If they've been on the drug for a while, this new drug, we're going to need a placebo. Okay, so we're going to have three groups. So group 1 is going to be our placebo group. And nobody will know whether they're in the placebo group or not. We'll randomly assign the subjects. Group 2 is going to be a low level or minimum level of a new drug to reduce Parkinson's symptoms. And this is going to be a higher level of this new drug. And this is going to be group 3. So we're going to have a large group of Parkinson's patients. Let's say they all have to be, the inclusion criteria here will be, they all have to be diagnosed within a year, brand new patients of Parkinson's. They volunteered to be in our study to see if this new drug will help reduce the number of symptoms. And so here's our large number of Parkinson's patients, and we'll randomly assign them to the groups. And then we'll have some way of measuring. Our dependent variable is going to be the number of symptoms, let's say in a week, on this new drug. And now, so some will just have the placebo, some will get the low level, some will get the higher level. We randomly assign them. That means any Parkinson's patient who volunteers to be in our study has an equal chance of being in all the groups. Our focus then to test that null hypothesis is we're going to have the mean number of symptoms, I'm going to just put S, for group 1, the mean number of symptoms for group 2, and the mean number of symptoms for group 3. Now, if the drug works, then the mean number of symptoms in group 1 should be greater, because they're actually untreated, greater than the mean number of symptoms in group 2. And if a higher level of the drug works, then we'll get the lowest mean number of symptoms in group 3 if the higher level works. If the new drug is useless, which is a possibility, then we'll see that these are all approximately equal, not exactly equal, approximately equal, and they'll only differ by tiny little chance differences. So we randomly assign the subjects, and then we count the number of symptoms. We have somebody, maybe a spouse or some independent observer, watch the person. Maybe they're recorded for a period of time during the day, maybe 8 hours, and then we count the number of symptoms from the recording, some kind of way to make the measure more reliable and less biased. So let's say, we have 15 symptoms, 14 symptoms. So these are all our patients. Patient 1, patient 2, the last patient in this group, patient K, patient 1 through patient K. Notice they're all different Parkinson's patients, patient 1 through the last patient. And if we randomly assign, let's say, 45 subjects to those groups, then the N here is going to be, of course, N1 is going to be 15 subjects in the group, 15 subjects in the group, and 15 subjects in this group. We'll go through all the steps of the analysis of variance. We'll form a source table, as I do in chapter 9 of my book, and you'll look at the source table to see whether there is a significant F value. Now, if these means vary beyond chance, what's going to happen is that F value that we obtain, this is our derived F value, or obtained F value, that F value will, if there's real differences and the drugs are working like we hope, hopefully it doesn't make it worse, because that's a possibility, then our F value will climb greater than 1. Usually 2, 3, 4, 15. In the real world, you usually don't get F values more than 5, 7, 10. But I have had situations where an F value might be even 100, a little unusual. And it really means that there's really large differences between the groups. And so we'll through those steps in the chapter, we'll obtain our F value. Here's our F value. And we're going to get this derived value. And let's say it's 2.95. It is greater than 1. So it looks like as this climbs and gets greater, it looks like our null hypothesis is false, that there are mean differences here. And so let's draw our F distribution. And so here's our F distribution. Remember, this is the F distribution, and these are our numbers on the F distribution. And remember, I told you this is going to be about F equals 0.00, this point right here. This is frequency, and this is very high frequency, very low frequency. And remember, it's a skewed distribution. And we're going to put 5%, our standard conventional level of statistical significance, 5% of the area under this curve. If we get an F value along here, remember I told you around here maybe is an F value of 1.00. Anything in here, we're going to retain HO and claim that there's only chance differences between our means. So this is retain the null hypothesis. And this region is going to be reject the null hypothesis. Notice that the F value that we derive is going to be on this line scale somewhere here. If it crosses this point right here, which is our F critical value at 0.05, we'll reject the null hypothesis. And we just place our F value, our obtained F value, on this distribution. Now, the F value changes shape for two reasons. One is what we call the degrees of freedom 1 is the number of groups minus 1. The second degree of freedom that we're going to need is df2, and sometimes they call this the numerator degrees of freedom. Sometimes they call this the denominator degrees of freedom. And this is going to be roughly, I'm going to do approximately, the number of participants, total number of participants, minus a few things, but you can look in the book for that part. So roughly the 2 degrees of freedom. This F distribution is really a family of distributions. And so it's going to change shape based on the value of df1, whatever that is. I'm going to put x, and the value of df2, sub 2, which is roughly the number of participants, and I'm just going to put y there. And that will tell us exactly at 0.05 what our critical value is that our derived value must exceed in order for us to reject HO. Now, the only bad news here is the analysis of variance is said to be an omnibus test. And what that means, omnibus means all. What that means is, for us, is if we reject, if our obtained F value, we plot it on here and the critical value is 2.45 and our value is 2.95, this critical value right here, if it's 2.45, then we'll reject the null hypothesis. But because it's an omnibus test, we don't know whether group 1's mean is different, greater than group 2, but group 2 is approximately equal to group 3. We don't know if 1's greater than 2, greater the mean for 1, greater than 2, greater than 3. We don't know if it's 1 less than 2, less than 3. There's also all these possibilities. So that's why it's called an omnibus test. So that bad news that I was hiding from you is, if our F is significant, which hopefully it is, because that's why we're doing the experiment to see if this drug really works, then we have to run another test after ANOVA. If we reject the null hypothesis, and that'll be in chapter 10, we have to do what they call, most commonly called a post hoc test. And that's Latin for after this. What's the hoc part? What's the this? Well, it's if you run analysis of variance and you find significance, that is, your F value falls in this rejection region, then you have statistical significance. You know there's at least one mean different from one other mean. And after analysis of variance, a significant analysis of variance, you'll run a post hoc test. And that will tell you which means are different from each other and which means are not. And it'll tell you what the pattern is. They're also called a posteriori tests. They're also called multiple comparison tests. I suspect this is the least popular name because it's difficult to pronounce. More popular is multiple comparison tests, also called post hoc tests. And the one that I kind of use the most, which is the most popular, is Tukey's test. John Tukey, American statistician, and he created a test that after ANOVA, and the nice thing about Tukey's test is it's a nice balance between liberalism and conservatism. If there's mean differences, it usually finds them, but it doesn't find a lot of chance differences and call them significant. So that's the nice thing about Tukey's. A nice balance between being liberal and conservative after your analysis of variance. And that's an introduction to ANOVA.